Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a very exponential equation. We have I to the power z to the power I equals 1. I guess the left hand side could be read as izi or izi, whatever. Wow, what an exponential, right? So let's see how we can solve this kind of problem. Again, there's going to be some ambiguity that I'm going to be throwing in there, and hopefully we can kind of talk about that. Great. Let's go ahead and see how we can solve this problem. I'm going to start by replacing I with its polar version. Notice that z is nicely squeezed between two i's, and obviously you can make up so many equations that are of this type. And this is the type of problem that you're not going to find in pretty much any textbook. Correct me if I'm wrong. Please comment down below if you are able to find any kind of equations like these in any textbooks, because I haven't seen any. But correct me again if I'm wrong. Anyway, so we have I to the power z to the power I, or izi, equals 1. And let's see how we can solve for z. Now, we're going to start by replacing I, the very bottom I, by e to the power I times pi over 2. Because that's basically the polar version, right? Thanks to Euler. But we can also write this in a more general form as e to the power I times pi over 2 plus 2 pi n, where n is an integer, right? Okay, again, like I said earlier, we're going to discuss different possibilities. So let's go ahead and plug this in and see what happens, because we're going to have other complications that we have to overcome. So now I'm going to go ahead and replace this I with e to the power I times pi over 2 plus 2 pi n. I want to use the more general form, and that's going to give me this to the power, of course that's just the I, and then I have to raise it to the power z to the I, which is another exponential, and it's supposed to equal 1 at the end. But we can also replace 1 with the complexified version of 1, which is e to the power I times 2 pi k. K is another integer. They don't have to be the same, but k is an integer, and if k is 0, we get e to the power 0, which is 1. If k is not 0, we still get 1, because you think about all multiples of 2 pi. They always give you 1 on the unit circle, right? Great. Now let's go ahead and exponentiate, and we're going to be multiplying the exponents here on the left hand side. So that's going to give us I times pi over 2 plus 2 pi n. That is multiplied by z to the I. And on the right hand side, we have I times 2 pi k. So what I did was basically set the exponents equal to each other, right? So if you have e to the power z1 equals e to the z2, does that not imply z1 equals z2? If you natural log both sides, that's what happens. But those numbers are actually separated by some multiple of 2 pi ki, whatever. But we already have that, so we don't need to introduce another level of complexity, right? So this should be good enough, and now let's see where this takes us. Notice first that I can be cancelled, right? That's good. I is not 0. We can cancel it out, and moreover, we can cancel pi. How? If you take pi out, you're going to get 1/2 plus 2n multiplied by z to the I, and on the left hand side, that's what we have. In the right hand side, it's 2k multiplied by pi. So that means pi is gone, and we have even a simpler expression. Guess what? The only things we have left are integers, right? K and n. Well, this is interesting. That's why I think this is a pretty good, interesting problem. Anyways, I talk too much. Let's go ahead and get to work. That's probably why I lose my voice once in a while. I shouldn't be overusing it anyways. So what should I do? Make a common denominator, and then multiply by the reciprocal, and that gives us z to the I equals 4k divided by 4n plus 1. Great. Now k and n are integers, so this takes many forms. For example, if k is 0, we get 0, which is not a good thing, right? Because, well, Is it not a good thing? Maybe it is. Who knows? Well, if k is 0, z will be 0, right? It's not super bad, actually. It's pretty good. Anyways, now, we still haven't found z, though. Let's go ahead and find it. Natural log both sides again. We're going to get I ln z, or use the complex exponential, whatever you want to use. And this is going to give you ln 4k over 4n plus 1, and finally we're going to divide both sides by I, but no, we don't do that. We multiply by negative I because it's the same thing. And when we do multiply both sides by negative I, we get something like this. So we kind of have like a multiple of I, which is a imaginary number in this case, but we still have to find z from here, ln z, and remember, z is e to the power ln z, and since ln z is already known, z should be equal to e to the power negative I multiplied by ln 4k over 4n plus 1. Remember, k and n are integers. When I said complications, this is what I was talking about. But notice that this can also be written as e to the power ln 4k over 4n plus 1, and then go ahead and raise it to the power negative I, and inside you're going to notice that, hey, this is equal to 4k over 4n plus 1, so isn't this actually equal to 4k over 4n plus 1 to the power negative I? What is this? I don't even know what it is. So let's go back, right? This is not good. Let's go back here, because this is definitely much better. Let's just totally forget about it, shall we? Now, what is this? This is e to the power I times something, which is super cool because that should remind you Euler's formula, right? What is e to the I theta? Cosine theta plus I sine theta. Beautiful. So if we can identify theta, we can go ahead and just plug it in, right? Let's go ahead and do it. So you can leave it in this form. That's perfectly fine because it's pretty compact, but we can also do the following. Using Euler's formula, we can write this as z equals cosine of ln 4n plus 1 over 4k. By the way, I just did a little quick trick. I used this as negative 1, put it here for the ln, and flipped it because something to the power negative 1 is the reciprocal, remember? So that's how I got that. Make sense? I hope it does. I didn't skip a step. I kind of did, but I explained it. Hopefully that'll be good. And now we're going to write it for sine as well using Euler's formula, and that should be the solution. Which one do you like better? Just let me know. But this second one is obviously much longer. So let's go back to some of the particular values we talked about and also go over some complications. And we'll be looking at some results from Wolfram Alpha if I did not forget to include them here. Sometimes I do forget. In a video that I made for my other channel, Cyber Math, actually there was a last slide that I forgot to mention, but I'll probably share this as a pinned comment or something like that. Anyways, did you know that I had another channel? Anyways, if you didn't, please check it out. Anyways, after this quick self-promotion, let's go ahead and look at some particular values. For example, if k is equal to 0, let me write the more compact version. And again, this time I'm going to use the flipped version so that we don't have a minus sign. Make sense? You see, these two are equivalent. Now, if k is equal to 0, that's not good. But in the original problem, if k was 0, didn't we get z equals 0? Was that the case? Let's go back and find out. Yes, if k is equal to 0, you got z to the I equals 0. So that should immediately imply z equals 0. But in this case, it's problematic. You don't want to divide by k. But the $1,000,000 question is, if z to the I can be found, and which I can find out, by the way. Let me show you real quick something real cool. I to the zi equals, I to the z to the I equals 1. And now remember, which powers of I are 1, right? You probably thought about this before me, but remember I to the 4 is 1, right? Or in general, I to the 4k is 1, where k is an integer. Beautiful. I mean, if you don't want to use the same k, you can use something else, but that's fine. So can z to the I be just equal to 4k? Then this would be satisfied. That would mean that e to the I ln z equals 4k, and then I ln z equals ln 4k. And then from here, you would be getting basically ln z equals negative I ln 4k, and then z would be e to the power negative I ln 4k, right? And in this case, if you set k equals 1, you would be getting, for example, z equals e to the power negative, k equals 1, I meant, not k equals 0, that you would be getting something like negative I ln 4. This would be e to the power ln 4 to the power negative I, which is 4 to the power negative I, so on and so forth. Anyways, hopefully you got the idea, and that should give you actually 1 at the end. But anyways, do we really need n in this equation, or can we just get away without using the n? And let me know what you think. And it looks like I haven't included anything. Well, I did. Guess what? There are many solutions. These are just some of them. And this brings us to the end of this video. Well, thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.